What I want to do in this video is I want to take the ideas that we've been developing over the last section and a half about span, linear independence, and the determinant of a matrix. And I want to kind of direct our attention at what that implies regarding a basis. So I'm not actually going to say anything new in this video as far as topics, but what I want to do is incorporate a lot of the ideas that we've talked about so far. So in particular, what I want to do is some things like the following. So let's consider the set, and I'm going to call it E. Let's say the vector 1, 4, 2, 3. And what I want to know is, so here's our question. Let me write this a little bit better. So what I want to know is E a basis for R2? And so what we've talked about so far and some of the ideas that we've developed so far really lead us to this idea of just looking at the determinant. Well, we just have to look at the determinant of the matrix that we get by taking these vectors and putting them as the columns of that matrix, 1, 4, 2, 3. And so the reason why we want to do that is that we want to know, as a basis, do these vectors span all of R2? So in other words, we want to know if I take, say, I want to use different constants. Let's say I take A times 1, 4 plus B times 2, 3. Can I write every possible vector, say st, as a linear combination of these two vectors? And so we talked about why it's enough to actually think of this as a matrix equation. So this is 1, 4, 2, 3, AB equals st. And then knowing the determinant actually is enough to tell us whether or not there's a unique solution here or whether there's any solution at all. And if the determinant is non-zero, then there must be a unique solution. In particular, every vector st can be written as a linear combination here. Since our determinant's -5, it turns out that this is the case. And indeed, these two vectors, 1, 4, and 2, 3, span R2. So the determinant being non-zero tells us that these two vectors span R2. On the flip side of that, the other thing that we need to determine in order to determine whether or not the set is a basis is we need to determine whether these two vectors are linearly independent or not. So I'm going to take a linear combination of these two vectors. So C1 times the first vector plus C2 times the second vector. And I want to know if this is equal to 0, 0, what are the solutions to that? Are there constants other than C1 and C2 both being 0 that give us a solution? If C1 and C2 being 0 are the only solutions to the system, then this is a linearly independent set of vectors. This pair of vectors are linearly independent. If there's other solutions besides C1 and C2 being 0, so if there's these so-called non-trivial solutions, maybe if C1 is 5 and C2 is -3 or something, I mean, it's not going to work. But if there were those non-zero solutions, then the set 1, 4, 2, 3, that pair of vectors would be linearly dependent. Again, it's enough to look at the determinant because you could write this as, again, a matrix equation, 1, 4, 2, 3, this time times the vector C1, C2. And then here we want to set this equal to the vector 0, 0. And really, these are the same idea that we're doing in both of these steps. If you look at the determinant of that matrix 1, 2, 4, 3, what that's going to tell you is whether or not this system has a unique solution, and you can figure out what that solution is by taking the inverse if you really care. We don't even actually care what the solution is. We just want to know, is there a solution? Likewise, we want to know in the second part, we know that there's at least one solution, but is the solution unique or are there infinitely many? Those are the only other options. And again, the determinant comes to the rescue and saves the day. So looking at the determinant is actually enough to tell us whether or not it's a basis because it does these two things at the same time. Okay, it tells us that yes, these two vectors span R2, and yes, these two vectors are linearly independent. And so since the determinant is non-zero, we can conclude yes, this set E is a basis for R2. So the determinant is actually a pretty powerful method here. It's a pretty powerful tool for determining whether or not a given set of vectors is a basis for a vector space. And let's do one more. And I'll show you kind of how this works. Let's look at the set of polynomials P2 And let's look at some vectors in P2. Let's say I want to consider the set of vectors 2x squared plus 4x. I want to look at x squared plus 1, and then I want to look at the vector 3. These are all functions, so this last one in particular is the function that's always equal to 3. It's a horse on a line with y value 3. And I want to know, is E a basis for P2? And it turns out that this is exactly the question that we were trying to look at before, except for a different vector space. And what we can do is, if you try and write this out, if you want to figure out whether or not these span, if you want to figure out whether or not these three vectors span all of P2, you can figure out if you take A times the first vector plus B times the second vector plus C times the third vector, whether or not this is equal to some generic polynomial, and we can call it whatever we want. Let's just call it alpha x squared plus beta x plus gamma. So is there, for all alpha, beta, and gamma, are there solutions A, B, and C so that these are equal? And so what this really amounts to is solving a system of equations. And the system turns out to be, we have 2a plus b times x squared. And this somehow, I'm sorry, is 4x. So this 4x squared should just be a 4x. I just copied that wrong, I think. So anyway, so this implies that 2a plus b, if I just look at the x squared terms, 2a plus b times x squared, our linear term is going to be just 4ax, and then our constant term will be b plus 3c. We want this to be alpha x squared plus beta x plus gamma. And so if we want these two polynomials to be equal for all values of x, because that's what it means for polynomials to be equal, is if we want that to happen, we want the coefficients to be equal. So really this means that we need to solve the system 2a plus b equals alpha, and 4a equals beta, and b plus 3c equals gamma. And this is a pretty straightforward system to solve, but it's even more straightforward just to know, really you just want to know whether or not there's a solution. For all alpha, beta, and gamma, you don't care what the solution is, just is there a solution? And so if you want to, what you can do is you can write this as a matrix, and the matrix that we would get will be 2, 4, 0, 1, 0, 1, and 0, 0, 3. That's going to be times the vector ABC, and we're going to set that equal to the vector alpha, beta, gamma. And we want to know, is there a solution for all alpha, beta, and gamma? So again, it's enough to look at this determinant. This determinant took us a little bit extra to kind of dig up what was happening here. But once you see what's going on, this is a lot more straightforward. So if you look at this 2x squared plus 4x, what I mean by it's more straightforward is that it's now easier to look at this set of polynomials and think of a matrix. And the matrix that we're going to get is by taking these coefficients of the polynomials, and those coefficients 2, 4, and then there's no constant term, so it's 2, 4, 0. Those are going to be the columns of this matrix. And likewise, the second polynomial is 1x squared plus 0x plus 1. And likewise, the third vector is 0x squared plus 0x plus 3. And so those coefficients are going to turn out to be the columns of the matrix that we're going to have to take the determinant of. And so it's enough to know, is the determinant of this matrix, I'm just going to do a little iPad magic and copy paste here, but is this determinant of the matrix 0 or not? And it turns out that this determinant is not. You can expand, I think the easiest case here is to expand along the third column or even the second row. And what we're going to end up with is minus 12, I think. So 3 times minus 4, so it should be minus 12. But it's not 0. So that means that yes, there's for every alpha, beta, gamma, we can find a solution ABC that satisfies this. That tells us that it spans P2. If we want to get linear independence, so if we want to check whether or not the set is linearly independent, we're going to do basically the same thing. And we're going to take this left side I mean, basically, let me just copy. We're allowed to basically just copy and paste here. And linear independence is a slightly different question with the same methods. Okay, my iPad magic is failing in real time here. So let's copy. There we go. And then what we want to do to figure out whether or not the set of vectors is linearly independent is we want to solve this equation not equals some generic polynomial alpha x squared plus beta x plus gamma, but we want to look at 0x squared plus 0x plus 0, because that's the zero polynomial. We're thinking about the constant function that's y equals 0. It's the horizontal line through the x-axis. And so if we want to set this equal to 0, this means that now we have to solve 2a plus b equals 0. It's basically, again, the same system, just with alpha, beta, and gamma all replaced by 0. So we're going to solve this system for a equals 0, b plus 3c equals 0. And again, we want to look at the system. It's enough to look at the determinant. I'm not going to write out the final step, but it's enough to think of this system as a matrix equation. Knowing the determinant of the coefficients is enough to tell you that there's a unique solution. And so by looking at the determinant, we know that the only solution is going to be when a, b, and c are all 0. And this follows since the determinant of this matrix that we showed above was minus 12. Okay, so these are the same steps that we were taking in previous videos to show that a particular set of vectors spans a space or that a particular set of vectors is linearly independent. Now that we need to worry about whether a set is both a spanning set and whether it's linearly independent, the determinant is going to be super useful, and we can actually do both steps at the same time.